What you're seeing now is electricity being generated from a temperature difference between those two water streams, meaning one side is hotter and the other side is colder. Thrown in the middle is a thermoelectric generator, and that uses the Seebeck effect to convert that temperature difference into a voltage. That's why we have the multimeter there on the left set up. On the right side, we use a thermal camera to record the same video, and as you can see, one side is going to be brighter, which means it is hotter, and the other stream is colder, which means it's a darker blue. But what if I told you that both streams are coming from the same faucet? So how can they be different temperatures? Well, the reason for that is because of this device right here. Let's look at it from another angle. From here, we can see the device is charging. So the faucet is on hot and it's feeding into that shell-looking tube device. But what is actually in there, and why are we running hot water through a hose so that the inside of this device gets a bright red? Well, to answer those questions, we have to start with some background. My team and I, HeatSink, took on a research endeavor as part of our Engineering Academy capstone course at our high school and focused on recycling heat waste, as most processes in the world are not 100% efficient as dictated by the law of thermodynamics. A lot of that lost energy is lost as heat. So what if we could repurpose that heat back into electricity or save it for a later use? That's me, Cameron Higgins, on the left side of your screen, and I'm applying an epoxy to the copper pipe to seal it to that PVC tube. The device is replicated from a Georgia Tech PhD student research paper. It uses phase change materials like salt to store heat in its physical composition during the melting process. The other half of our team, since we were a group of 4, was focusing on creating more efficient thermoelectric generators. Because it's made of P and N-type material, crushed P dot was put under an electron scanning microscope for data analysis, and it was made using a process called electrospinning. But what is electrospinning? And what is the objective of this engineering capstone course? The course is dedicated to a year-long research project under nanotechnology, education, and research, which consists of multiple teams, and each team will choose a global problem. They will look at who it affects, why it affects, and why aren't current solutions working. Then at the end of the year, we give our annual engineering symposium where we present our research to the district. Throughout the course of a year, we go from this
is getting a PVC tube and running a copper pipe through it and stuffing the shell
to this.
Good evening, everyone. My name is Cameron Higgins.
And I'll let myself explain the rest to you.
Day before the symposium, we are cutting our posters, mirror posters, this is a Visiray poster, transparent solar cells.
Hello.
She's cutting it. So we can set it up on our easels. This is the heatsink poster. We're also going to start our demos, our procedure.
Stop fucking pushing it all.
Conclusion. My bad. He's cutting.
I was talking to Broad Stevens.
Thermal capture. This is where the easels and the posters are going to be. We're setting our bins up because we're going to have demos basically of sodium polyacrylate and the phase change salt, which is the Glober salt. This here is the sodium polyacrylate. It basically absorbs like 50 times its weight in water. And this is going to be the salt. We're going to have it on a heat table. Heat up the salt and show how it changes from its powdered form to its more liquid form. Because it's 1 part salt, 10 parts water. This is the electrospinning process. Basically, you would have your polymer. Yeah, these are Invisaray's solar cells here. So when you electrospin, you have that hot lamp on. It's a heat lamp. You have your polymer inside, which is in the syringe, and there's electricity. I think it was like 240 volts. So when you turn that on, 240 volts, you have the positive end. This side is with an aluminum foil, and so the aluminum foil is electrically charged. So the polymer basically jumps across onto the foil, and that's how you can collect the polymer samples, and it becomes a solid because the heat is evaporating the moisture from the mixture. This is just the vent hood. They're getting ready for the symposium. We have our grid tech, and we have HeatSink. They run the computer and the power supply. And this is our poster here. I'm going to do a demo of this is the hotbed, the sodium polyacrylate, and the Glauber saw here. We have more teams, electrospinning and duct over there, PFAS fetch. We have the tensile strength tester there. That's for our Tech. Tonight, this is the night of the symposium. It is it's soon actually, soon o'clock. It is 6:14. Our tables are ready. Symposium starts at what, 8, 7?
6:15. It starts at 7.
Starts at 7. We
Goes
have
up at
the
7:02.
electrospinning on. You can see the wires here that connect to the aluminum foil. The light is on. We have the scanning electron microscope. So it scans with electrons basically, because the regular microscope uses light and some things are smaller than the wavelength of light. So this is able to see down, I can't remember the max number. Here's some images here. So you can look at things in detail that are smaller than the wavelengths of light, which is pretty cool. A bunch of multimeters here for thermal capture. That is the thermal camera that we used also. Here's a regular microscope here in color. Now the scanning electron microscope, because it uses electrons, the image isn't in color because it's smaller than color itself. Over here, Silo Green is creating bioplastics. So that's their bioplastic there.
Good evening, everyone. My name is Cameron Higgins.
I'm Natalie Dunman.
My name is Max Brodsky.
I'm Charlie Hawthorne, and together we are
HeatSink.
Waste costs money. Have you ever had a laptop on your lap and felt it start to warm up, or tried to use your phone and have it overheat and fail? You've been a victim of waste heat. That heat getting released, the energy for that could have been used for tons of other things. As electricity, it could be lowering your power bill, it could be extending your battery life for your devices, or it could be saved to heat your home during the colder times of the year. You can see that the price of electricity has increased for both consumers and for commercial businesses for the past several years, and this is outpacing inflation, indicating some other cause. The biggest one is that the supply has not been keeping up with demand. As you can see, 60% of all consumed energy is reproduced as waste heat. So if we were able to recycle even a small fraction of that, then we could reduce energy costs and help reduce pollution and other fossil fuel burning and other byproducts.
Several solutions are already in the works for this. At the industrial level, these include back pressure turbine systems, which reuse steam that has already passed through a turbine to generate electricity by reallocating its residual waste heat to various industrial processes, before finally reheating the steam in a closed cyclical loop. Another solution is data center heating, in which excess heat from data centers is repurposed for the heating of residential and office spaces during the colder months of the year. However, both of these solutions suffer from a lack of use due to the various expenses and infrastructure adjustments that their implementation would often necessitate.
A solution that we utilize in our experiment is the Carnot battery. The Carnot battery, or phase change material battery, stores thermal energy for long durations of time to be converted into electricity for later use. This method of heat conservation relies on phase changes. When a substance undergoes a phase change, it will sometimes absorb heat to do so. This latent heat is stored in the battery as thermal energy.
We also made use of thermoelectric generators, which can get the heat out of the PCM battery and convert it back into electricity. These use the Seebeck effect, which converts the temperature difference between two sides of a conductive material into voltage, which then drives current and generates power. For a thermoelectric generator, you want high electrical conductivity for the electrons to flow, and a low thermal conductivity so that you can maintain that temperature difference for constant power generation.
Following these principles, we wanted to create a phase change battery storage. So we came across a research paper by Dr. Jason Hershey from Georgia Tech and emailed him of how we can replicate this in the high school. Some of the substances here may seem alien to you, but the first one is expanded graphite. That is a heat-treated and acid-treated version of graphite. On the right is borax, which is the nucleating agent. It makes sure that the phase change material, which is the sodium sulfate decahydrate, stays in optimal temperatures for freezing and melting. And then the sodium polyacrylate is an absorbent used in diapers. That is so we can absorb the phase change once it melts.
To create a functional PCM battery, we used a shell and tube structure. To do this, we cut a copper pipe to fit onto a larger PVC pipe. Then we used PCM and poured and compressed it into the larger PVC pipe. The copper tube was sweated on both ends so that a hose could be attached to it, which you will see later on. To ensure that the PCM did not leak out, we sealed the tubes together using steel epoxy. To charge the thermal battery, we ran a hose through one end of the copper tube and then ran water through it into the battery. As the hot water ran through the battery, some of the PCM inside absorbs that heat. And as the PCM reaches its maximum energy capacity, it begins to melt.
Because the phase change system is absorbing the energy from the water, the output water is going to be cooler than the in-stream. So we set up a dual stream system from the faucet and placed a thermoelectric generator in between them. Now we were working with around 52.8 degrees Celsius water and a 2.5 degree difference. From our results here, in 800 seconds, we were able to store 0.39 joules using the efficiency of the thermoelectric generator. And on the release, we were able to get a power output of 3.7 milliwatts. Now with a thermoelectric generator that is not commercial and higher end, like 12%, that would quadruple our results.
In addition to using TEGs with phase change material batteries, we wanted to understand them better and see how they could be implemented into common devices like computers and phones. So we had an experimental setup with thermoelectric generators inside a computer between the CPU, which provided the hot temperature side, and the air cooler or water cooling loop, which provided the cold side. We compared new and old commercial TEGs, and we also used different ways of cooling them and measured the power generation statistics. We found that the better it could cool itself, the more energy it could produce. Because while we found that a higher temperature difference does generate more power, what is also important is making sure that it stays cool and doesn't thermally bottleneck. We also found that the higher temperature difference can lead to advanced material degradation. You don't want your computer to be sitting at 100 degrees Celsius all day. That's bad for it. So it's important to balance those statistics to get a balanced production of electricity. You can see here, like I said, at the same temperature difference, we were able to get 4 times the power using better cooling and thermal interface materials because we reduced the bottlenecking. Like it's 90 milliwatts versus 25.
Building on our research with prefabricated commercialized thermoelectric generators, we set out to make our own. To do this, we used a PDOT PSS aqueous dispersion, which is essentially a solution that contains PDOT, which is currently the most thermoelectrically efficient known organic compound, and PSS, which is an additive that increases its solubility and also acts as a counter-ion during thermoelectric conversion. We electrospun this solution into thin nanofibers of into thin P-type thermoelectric nanofibers that, when a heat source is applied to them, drive positive charge carriers away from the source of that heat, generating a current. We characterized it very similarly to our commercial TEGs by measuring power and temperature statistics over a testing period. And these were really only meant to serve as baseline measurements, as there are many improvements that could be made to our simple construction of our TEG. Even for a baseline, though, our results were very, very promising. We were able to maximize our power output at around 10 milliwatts while sustaining reasonable temperature on our computer. And this is promising because though it is only about 1/10 of our commercial peaks, our TEG was made with much fewer materials. It was much cheaper to produce. It is also much smaller, and there are many modifications that can be made to it to increase its efficiency, such as using a thermally conductive casing, using thicker fiber mats or layering them, or including an N-type fiber in alternated electrical series with the P-type fiber.
If we had more time, we would experiment with synthetic zeolites, since unlike our PCM battery, they're able to hold heat for a virtually infinite amount of time.
Additionally, we'd continue researching thin-film thermoelectric generators and modify many of the material properties previously mentioned in order to increase their efficiency. Finally, we'd use these technologies in tandem to develop a more effective solution for waste heat that can maximize the output of both of these unique technologies.
So what does this mean for consumers? Well, if we look back into the 1960s, computers were the size of an entire room. Nowadays, they fit into your pocket, and some even fit on your wrist. Right now, we have a 28-inch long thermoelectric storage system, and in 16, 10, 65 years, what could be done then? Could innovation shrink it down to the size of a AA battery? As you've seen, the performance are comparable. That could save you hundreds on your electricity bills during the summer and the winter. We would like to pass it off to thermal capture and thank you for your time.